Well, it doesn't grow on top very well. The sides keep growing, but that's the part I don't want to grow.
Mine's vice versa. It's like, this grows, the sides grow the slowest.
Oh man, because then it starts messing with your ears and stuff. And I wear a CPAP machine for sleep apnea at night, so then you can see all like the lines. I mean, at some point you get to a certain age, you just stop caring. But my wife yells at me.
Yeah, my dad feels the same way. Like, he got the lines on his face, and he wakes up and not
All right. Let's see. Homework for today was function version of FizzBuzz. Okay, so last time we talked about, I'm just going to delete all this crap. Last time we talked about the idea of writing functions, and when we might want to call upon some logic multiple times, we can write a function that takes some parameters, we can pass it that parameter, and it gives us our answer. We can do what we want with that answer. Remember, we kind of talked about the difference between returning a value and printing a value last time. So lately, been working with this logic, this this made-up stupid FizzBuzz logic. So what we're going to do today is we're going to bring that logic into a function that allows us to test a single number. You pass the function a number, it tells you whether it should print out fizz, FizzBuzz, buzz, or just a number. All right, so it's kind of like you went to Home Depot and you got a little tool that you could just drop a number into and it spits out the correct FizzBuzz logic number. All right, so we're gonna define a function. I'm just gonna call it FizzBuzz, and this guy is gonna take in a single parameter. We'll call it a number, and then we want to start asking some questions about this number. So we're gonna say if the number is evenly divisible by 3, which means it has a remainder of 0 when I divide it by 3. And, what is it, in Python 3, it's and like that. Number mod 5 is equal to 0. I know some people did the number mod 15 equals 0 and just said that's good. That's fine. The math works, but this gives us practice using and. So if both of these are true, if it's evenly divisible by 3 and it's evenly divisible by 5, then we can say return FizzBuzz. We're going to choose to have it return the value, not print the value. Else if number mod 3 is equal to 0, we'll return fizz. Else if number mod 5 is equal to 0, we'll return buzz, else. Just return the number. And if you wanted to keep everything as strings that are coming out of this, you could say I'm going to return the string version of the number. But Python does not make you do that. Being a loosely typed language, I could have my return type of this function be strings most of the time. Well, actually, it's probably strings some of the time, and then an int the rest of the time. That's allowed in Python. If I were writing this in Java or C++ or C#, I would have to define FizzBuzz to be a function that returns a kind of value. So in this case, since I'm returning strings sometimes, I would have it return a string, which means when I got down to return my number, I'd have to convert number into a string. All right, so I would call this good programming practice, would say consistently return the same type from your functions. Python will let you get away with it, but this function will always return a string, as I have it written right now. All right, so now right now, this is an untapped resource. If I hit play here, my program does nothing. If I want to get FizzBuzz, and I want to pass it the number 16, for instance, and I hit play, what will my output be? What's FizzBuzz on 16? Is it evenly divisible by 3 and 5? No. Is it evenly divisible by 3? Is it evenly divisible by 5? So it's just going to give me a 16. So of course my output is nothing. Why is it nothing? Because this function returns a value. It does not print a value. So this guy right here boiled down to 16 and I did nothing with it. If I want to get the answer from that, I have to print out the result of that. And there's my 16. Similarly, I could put it into a variable. I can say answer is equal to FizzBuzz of 213. And then I can print answer. What do I do? Misspelled FizzBuzz. Spelled it fuzzbuzz. So there's fizz. So that guy is evenly divisible by 3, but not the other ones. Make sense? So that's me doing some logic, returning a value, and then I can choose what I want to do with that returned value. So now we're supposed to do what, all the numbers between 1 and 100,000? So for I in range, this is outside of this function. So this is my program part of it. This is I ran to Home Depot and I bought this little tool called FizzBuzz. All right. Okay. Although instead of running to Home Depot, I made this one homemade. Right. So I made my own function called my own little tool in the garage called FizzBuzz that I can drop a number into, a single parameter. I can give it any input, any numeric input, and it will return for me one of these outputs. So now I'm going to send it a whole bunch of inputs by repeating a step a bunch of times. So I'm going to say for I in range 1 to 100,001 if I want to get all the values between 1 and 100,000. So now each time through here, I will be the next value. So the first time through this loop, I will be 1. Then it'll be 2. Then it'll be 3. Then it'll be 4. That's what this for loop does. This for loop takes I on a journey between this number and this number minus 1. All right. And then each time through, I'm going to go ahead and print out whatever FizzBuzz returns for the current value of I. I'll take my value of I and I'll pass it to my FizzBuzz function. My FizzBuzz function will figure out what the answer is going to be. It'll spit the answer back out. This guy will become the result. And what am I going to do with that result? I'm going to print it. See how that's working? Now, we have messed with string concatenation a little bit, so I could actually cheat here. And I could say something like answer is equal to the empty string. And then I can say answer is equal to answer concatenated with whatever FizzBuzz returns, concatenated with a carriage return. And then print out answer a single time afterwards. Let's see, answer is equal to FizzBuzz of I. Yeah, there we go. So there's my answer. Took a second to run, but you saw that it ran a lot quicker than if I printed every single time. So in this case, I'm actually only printing one time. And what am I doing each time through? I am building up a string that started off as nothing, and I kept adding to it my current answer of FizzBuzz plus a carriage return. Not that big of a deal. Just instead of it taking probably 15 minutes to run through all 100,000 numbers, it did it in, 20 seconds or something like that. All right. So, question about what we did, or questions about what we did here, and then how we used it down here. Go ahead.
Yeah, what happens if we put print instead of return for the return FizzBuzz?
These guys?
Yeah.
Yeah, so now instead of this guy coming down to an answer, so here, let's go back to our original thing. So if I say print answer here, and then up here, you want to put prints in here. So this is print being different than returning. And I don't even have to turn it into a string now because it's never going to leave this function. Okay, this function now does not return a value. Instead, I pass a number in, it goes through the logic, and it will display the answer for that. Now, I'm printing out FizzBuzz of I here. That's what my logic originally said. Print out whatever this function returns. This function returns nothing. This function prints some stuff. Printing is different than returning. So what I'm going to see is I'm going to see the answer from FizzBuzz get printed to the screen. And then, well, the output of FizzBuzz printed to the screen, and then the answer of FizzBuzz, which will always be none in this case, because this function does not actually return anything. So I'll see nuns wrapped inside there. Go ahead and stop this. You see how we have fizzes and numbers and nuns. So this guy right here always printed out a none. Inside, it printed out its own output. But output is different than giving an answer. All right? One is not better or worse than the other. It depends on what you're trying to do. Okay? You might maybe the better naming convention for this guy would be called display FizzBuzz. And maybe there'd be another one called get FizzBuzz. Get FizzBuzz hands you the answer of that you can do whatever you want with it if you want to do math with it or concatenation or something like that. Whereas display FizzBuzz just spits something out to the screen, but doesn't give you the opportunity to use that value for anything later on. Does that make sense? Because we might want to, for example, let's call this get FizzBuzz. Have this guy take in a number. We'll steal our logic there and then take the prints off. Make this return. And I'll go back to the string version of this. All right, let's say that what I want to do in here is actually count the number of fizzes that come out of it. I want to know how many fizzes it found. All right, calling get FizzBuzz will give me a result that I can then say, was the result it gave me equal to fizz? If it was, I can do something with it. But if I call display FizzBuzz, I will not know that. So we name this guy display FizzBuzz, and maybe I ask a question about that. We're going to call number of fizzes. And we'll start off with 0. We found 0 fizzes so far. And I'm going to ask a question. I'm going to say, if display FizzBuzz of I is equal to fizz. If that's a true statement, I'll say number of fizzes is equal to number of fizzes plus 1. There's some shorter ways of saying plus 1, but I don't know if the book's introduced it yet. And then after this for loop, I'll go ahead and print out number of fizzes. What will the output of this program be? What does display FizzBuzz return? What does it return? Now, what does it output? What does it return? Here's display FizzBuzz up here. It returns nothing. So I'm going to get the value none out of there every single time. How often does none equal fizz? Never, right? None and fizz, different values. All right. So this is going to give me, oh, probably didn't want to have the prints in there. Trust me, in the end, it's going to give me a 0. It found 0 fizzes returned by display FizzBuzz because display FizzBuzz might print out fizz a bunch of times, but it doesn't actually return it. Now, if instead I call get FizzBuzz, this guy I pass the number to, he does his math, and then he returns a value to me that I can then test. So if I call get FizzBuzz instead of return FizzBuzz, I found 26,667 fizzes. If instead I wanted to search for fizz buzzes, 6,666 fizz buzzes. If I want to just search for buzzes, I get that. If I want to count all of them, I can say number of fizzes, number of buzzes, number of called FBs, and then number of numbers. So now I'll go through here and I'll ask a question. I'm going to go ahead and get my answer. I'll say answer is equal to whatever FizzBuzz returned there. So I have my result from FizzBuzz. Now I want to test that result. I want to ask some questions about that result. I'm going to say if answer was equal to fizz, then we'll say number of fizzes plus equals 1. That'll add 1 to it. Is the book talked about that already? The plus equals thing? So this is equivalent to saying number of fizzes equals number of fizzes plus 1. Just a shorthand version of saying it. Else if answer is equal to buzz, number of buzzes plus equal 1. Else if answer is equal to fizz buzz, number of FBs plus equals 1. Else number of numbers plus equals 1. And then in the end, I can just print out the result of those values. So here's my number of fizzes. I'll just do it. Number of buzzes. Number of FBs. Number of numbers. So I'm going to go through all the numbers between 1 and 100,000. Call get FizzBuzz, storing the result in answer. I'm remembering something. Remember, human beings solve problems by remembering things, asking questions, and repetition. Here I am repeating something 100,000 times. Each time through, I'm going to remember the result of calling this function. Then I'm going to ask some questions about that result. If the result of answer is equal to fizz, increment some value. So remember a value, change the value we're remembering, so on and so forth. And then in the end, I will just print out all those counts. And these should add up to 100,000. So 53,333 of those things were just numbers. Make sense? Go ahead.
What if you return a printed answer?
Okay. So what if you, let's just do a simplified function here. So I'll define, actually let's write it up here. define, do something. And this guy will take in no parameters. And we're going to return print hello world, something like that. So you're saying, what if I return a printed answer, right? That's what you're asking. So I'm printing something in here, hello world, but I'm going to try to return that. Okay. The question is, what does that boil down to? It displays hello world to the screen, but it will boil down to none because print doesn't return a value either. Somebody else wrote this function. Just like we wrote do something, somebody else wrote print. And print takes a single parameter, that is the thing we want to print, and it will print it to the screen. That's what we expect print to do. We don't expect print to resolve to a value. So if I return the value from do something, I say print do something like that. Do something comes in, it prints hello world to the screen. So we will see hello world to the screen. It will return the result of printing hello world to the screen, which should be none because the print function returns nothing. Then I'm printing out the value that was returned. There's hello world, and there's the none, which is the result of calling print. Does that make sense? Or not really?
Like when I ran it with the FISPA stuff, it worked.
Uh,
So like I had that equation stuff, then I put return at the bottom.
I'd have to see the actual code because it wouldn't just accidentally work. Yeah, print always returns none. It will display stuff, but it always returns none. So I believe you that your output is what you expected your output to be. But I also promise that your code is what dictated what that output was supposed to be. So you must have done something a little different here, or your output just happened to match up. But if you're printing out the result, like here, I'm printing out the result of a print. So if I just say print LOL like that, I'm going to see hello, or I'm going to see LOL to the screen because that's what this guy does. He prints something to the screen. But then I'm printing out the result of this function call. This function call happens to be the function called print, but the result of the print function call is none. So there's my LOL, and then there's my none. And that's not something special about print. I could do the same thing here by saying string 123. That'll convert the number 123 to a string. Actually, this one will be string of 123. We expect that to return the string version of 123, right? So it doesn't do anything itself. It instead spits out a value, which I'm then printing. So this function here, str, we know it's a function because we have an opening and closing parentheses here, is no different than the print function, except the print function's job is to take in a value and display it to the screen. That's it. The string function's job is to take in a value, convert it to a string, and then send it back to you, return it to you. So in this case, this will print out, the returned value from that function call, which is the string 123. And we know it's the string 123 because I can concatenate onto it ABC. And now I get 123 ABC. All right, so I'd have to see the code to see why it was doing that, but 100% of the time, this is how it works. You won't have situations in any programming language where you get like inconsistent results from code. Go ahead.
When you have print statements, what if you wanted to have the apostrophe or quotation mark within the print statement, but you didn't want to end the code?
All right, so you want to print something like A, B, double quote C, something like that. You would put a backslash before the double quote. It's called the escape character. This says, do not resolve this. I want that guy to be the double quote. Don't treat it as the string termination character. So this will give me the AB double quote C. And that'll work for any other thing that would otherwise mean something to the language. Single quotes, things like that. Plus signs. Although plus signs wouldn't be resolved inside of a string. You could put a plus sign in here. The plus sign is meaningless to strings, so that's not going to try to terminate that string or anything like that. So we'll get AB plus C as my output. All right, any other questions? And these are all good things. This curiosity and wondering that you got weird output, or like I think I pointed out a couple different times in class, what's tough about, I think I pointed out when we were talking about that something to a power, and that actually does a bitwise exclusive OR. But what sucks about it is it actually does give you an answer, so you don't get an error. You just get the wrong answer. So this is part of that debugging and learning programming as a skill set type thing. Again, this is kind of like a sport where sometimes you'll get an answer that looks like the right answer. It might even be the right output, but for the wrong reason. Something like that. All right, so something to be careful about, but definitely be inquisitive about it and test your code by writing different things, stuff like that. All right, any other questions? All right, so I think the homework for Wednesday is to write another function. So again, we're practicing with these functions. I think that one's what, area of the circle? Okay, so look up the formula for the area of the circle. I say you can use 3.14 as pi. If you want to use a more precise version of pi, that's fine. There is pi, a pi constant built into Python is probably like math.pi or something, but you don't have to go look that up. Just 3.14 is good enough. Okay? Just hard code 3.14 for your pi, and that'll be fine. But also pay close attention to how do you square a value. It's not the caret, right? All right, so let's go back and keep talking about our number bases. So last time we talked about this idea of the different bases that are involved in computing. So human beings are a major part of computing. We're the users, right? But for us in here, we're the programmers. We're the people telling this thing what to do. And we like base 10. So as often as possible, we want to operate with our base 10 number system, even though under the hood, it might be treated differently than that. Okay? Computers use binary base 2, which have legal bits of 0 to 1. We have legal digits 0 to 9. That's the language of base 10 numbers is 0 to 9. The language of base 2 numbers is 0 to 1. The language of base 16 numbers is 0 to 15, but that's represented as 0 to 9 and then A through F. And those are called hextets, but we can just think of it as the language of. The language of the octal number system is 0 to 7. So it's 0 to whatever the base is minus 1. But it's always represented as a single character. That's why hexadecimal requires us to go A through F instead of 10, 11, 12, 13, 14, 15. All right, so now we want to learn the patterns of converting these. The good news is, just like we saw with number conversions, apparently for the second time, we will use the identical pattern from going from decimal to any base as we'll use from going from any base back to decimal. Doesn't matter what the base is. We'll use the same formula. All right? So let's look at, for instance, let's go to binary to decimal first. So let's say I have the binary number 1011. Now, is that a legal binary number? Does that only use the bits that are part of the language of binary numbers? Is that a legal octal number? Yeah. Is that a legal decimal number? Yep. Is that a legal hexadecimal number? Yep. So we can say, oh, well, you only use zeros and ones. Did you probably mean binary? Yes, but we are reliant on the user to tell us what the base is. Okay. Or I usually will just write it as binary to decimal, something like that. because 1011 is a legal value in all the bases, except base 1. Base 1 only has zeros. So you just count the number of zeros. But we don't use that one. That's would be rough. If you did all your math, that's just counting. All right. So we want to say 1011 binary to decimal. So the pattern for this is we're going to go ahead and we're going to write out our bits with some spaces. Now, this is true for any number. We're going to see the patterns here in a second. This is 2 to the 0th power, 2 to the 1, 2 to the 2, 2 to the 3. So this is 2 to the 3rd power. This is 2 to the 2nd power. This is 2 to the 1st power. This is 2 to the 0th power. It's 2 because we're working with binary. Regardless of what base we were working with, it would be the base to the 0th power is this place. The base to the 1st power is this place. The base to the 2nd, the base to the 3rd, the base to the 4th, so on and so forth. We're going to write this a different way. This is the 1s, 2s, 4s, 8s place. This is 8, 4, 2, 1. 2 to the 0 is 1. 10 to the 0 is 1. 16 to the 0 is 1. Anything to the 0 power is 1. This is in the 1's place. This is in the 2's place. This is in the 4's place. This is in the 8's place. Since we're doing base 2, it's this number times 2 is this number times 2 is this number times 2 is this number. If we were dealing with octal, it would be times 8. If we were dealing with hexadecimal, it would be times 16. All right, and then what we do is we add it all up. So this is 1 times 8 plus 0 times 4 plus 1 times 2 plus 1 times 1. So that's 1 plus 2 is 3, plus 0 is still 3, plus 8 is 11. So 1011 in binary is equal to the decimal number 11. All right. Now I'm going to take this exact same slide, and we're going to say, we're actually going to treat that number as an octal number. Looks a lot like binary, because it's only using zeros and ones, but in fact, it's an octal number. So this is 8 to the 0, 8 to the 1, 8 to the 2, 8 to the 3. This is the 1's place, the 8's place, the 64's place. What's the next one? 256? 512. 512's place. So this is 1 times 512 plus 0 times 64 plus 1 times 8 plus 1 times 1. So that's 521. So 1011 in octal is equal to 521 in decimal. Make sense? Same exact pattern. Decimal to decimal. We might say, this seems like a waste of time, but we'll also see the pattern does work. This is 10 to the 0's place, 10 to the 1's place, 10 to the 2's place, 10 to the 3's place. So this is the 1's place. This is the 10's place. This is the 100's place. This is the 1000's place. Should remind us a little bit of, like, I don't know, what, second grade? Whenever we learned this, something like that. All right, so this is 1 times 1 plus 1 times 10 plus 0 times 100 plus 1 times 1,000. That's 1011. 1011 in decimal. Identical pattern if I'm going from any base to decimal. Make sense? Now, sometimes when you're dealing with bases, I'm going to steal this guy again just since I already have some spacing in there, but we're going to change this up. I'm going to go with my favorite hexadecimal number. Hex to decimal. So this is B, A, D. So this is 16 to the 2's place. This is 16 to the 1's place. This guy is 16 to the 0's place. I'm sorry. Which makes this the 1's place, makes this the 16's place. 256, yeah. 256 place. But now we have a little bit of problem. What's the math if we say B times 256? Well, we need to convert B, A, and D into their underlying values. They are single character representations of the language of hexadecimal. So a B is an 11. An A is a 10. A D is a 13. So the values for hexadecimal are 0 through 9, A through F, where A is a 10, B is an 11, 12, 13, 14, 15, F is a 15. All right, so it's a single character placeholder which maps to a, in this case, 2-character number. So now this is 1 times 13 plus 10 times 16 plus 11 times 256. And that is 2989. So 2,989 decimal equals bad in hexadecimal. All right, so we see identical pattern to go from any base to decimal. You don't have to memorize it for the different bases. Other direction. If I wanted to take, let's go up to this one, the number 11 and convert it to binary. So this is the other pattern. 11 decimal to binary. What we do is we take the value and we repeatedly divide it by 2, in this case, since we're going to binary. We record the remainder and we record the quotient. So 11 divided by 2. How many times does 2 go into 11? 5 times. 5 times 2 is 10, with a remainder of 1 to get us to an 11. 5 divided by 2. How many times does 2 go into 5? 2 times. 2 times 2 is 4, with a remainder of 1 to get us to a 5. 2 divided by 2. How many times does 2 go into 2? It goes in 1 time. 1 times 2 is 2, with a remainder of 0. We have no difference between 2 and 2. One divided by 2. How many times does 2 go into 1? Goes in there 0 times. 0 times 2 is 0, with a remainder of 1. We know we're done when we get to that 0. This tells us we have finished our conversion. And then we read our answer from bottom up. 1, 0, 1, 1. That's the binary version of the decimal value 11. Now, for relatively small values, you could probably kind of figure out, how to get an 11 or something like that by saying, well, what's the biggest power of 2 that's not greater than that? And then start putting 1s in those places. But this pattern here will always work. All right. Similarly, if I go off of this guy here, and we're saying 521. Decimal to octal. We'll follow the exact same pattern. Start at 521. We're going to divide by 8. 521 divided by 8 is 65. 65 times 8 is 520. So we have a remainder of 1 to get to 521. 65 divided by 8 should be 8. 8 times 8 is 64, with a remainder of 1 to get us to 65. 8 divided by 8, 8 goes into 8 one time. 1 times 8 is 8, with a remainder of 0. 1 divided by 8, 8 goes into 1 0 times. So we know we're done. 0 times 8 is 0, with a remainder of 1 to get us to 1. We know we're done. We read our answer from bottom up, 1011. So that is the octal version of the decimal number 521. Make sense? Identical pattern. $29.89 decimal to hex. $29.89 divided by 16, since we're doing base 16, is 186. 186 times 16 is 2976. So that's a remainder of 13. 186 divided by 16 is an 11. 11 times 16 gets us 176. So we have a remainder of 10 to get us to 186. 11 divided by 16. 16 goes into 11 0 times. 0 times 16 is 0, with a remainder of 11 to get us to our 11. We know we're done because there's a 0 here. We read our answer from bottom up, 11, 10, 13. But an 11 is actually a B, a 10 is actually an A 13 is actually a D. B, A, D. All right, see how that's working? So we only have to memorize 2 patterns. And then remember that any 2-digit numbers have to be mapped as letters. All right? But now we get back to our question of why are these the common bases for values in computers? Now, we saw here, if we go down to our $29.89 in decimal can be held in a more compact way with BAD. That seems good enough. We often use hexadecimal values in computers when we're indexing places in memory. because we have a lot of buckets in memory. Inside of our computer, memory is one gigantic street. All right? So if you have 16 gigabytes of memory, that is, and we want to have byte size. How many bytes is 16 gigabytes? That's 16 times 1024. That gets me megabytes times 1024. That gets me kilobytes times 1024. That gets me bytes. So 16 gigabytes is 16 times 1024 times 1024 times 1024. So that is, 17,179,869,184. So if I want to get to the last house on the street, I have to go to house 17,179,869,183. Because the first house is house 0. That's a pretty big number. But if I represented that value in hexadecimal, it would be smaller. It would still be a big, scary number, but it would be more compact. And it's those hexadecimal values that human beings are not comfortable with that make memory inside a computer scary to us, even though it's just a number. Okay? So, that's why we use hex. What if I were to ask you to take the value 1011101 from binary to hex? We could do it, right? We would first take that from binary to decimal, then go from decimal to hexadecimal. So we can do this the long way, or there's a shortcut. Similarly, I can take the value, so let's just steal this slide. One zero one 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 zero one from binary to octal. I could do this the long way, convert this number from binary to decimal, like we just looked at, then go decimal to octal. Or we can do it the short way. We'll look at the shortcut next class. All right, and that will explain to us why octal and hexadecimal are in play. All right, binary is in play because of decimal, or because of digital logic, zeros and ones, ons and offs. That's the language of the computer. Decimal is the language of the human. So now the question is why are those other two popular? All right, and it's got to be specifically those other two. We could also go to base 32. That would be also allowed for our trick. All right, I will see everybody on Wednesday. If you notice, tomorrow night is Raspberry Pi and movie night across the hall at 109, 5 to 6 p.m. I'm helping everybody get their Raspberry Pis set up on the network and also be able to remote into it and use it. Well, just connect it to your laptop, not having to plug it into a monitor. Then we're watching that movie, Art of Self-Defense. That'll be in 109 across the hall.